Concrete begins its life as a fluid mixture of cement, water, sand, and gravel. Concrete can be cast into molds or forms and will harden to create the necessary components of a concrete structure. The setting and hardening of concrete is caused by a chemical reaction between Portland cement and water. This can be demonstrated by adding a small amount of cement to water containing an indicator. The rapid development of a blue color reflects the release of hydroxyl ions from the dissolving cement. The chemical reaction between cement and water is called hydration. The dissolving cement increases the levels of calcium and silicon in the solution. When the concentrations of dissolved species reach critical levels, new solid products are formed through a precipitation reaction. This is a sketch of cement grains suspended in water. The solid hydration products form coatings around the particles of cement and gradually fill the space between. When the coatings first begin to impinge, setting occurs. There is a steady development of strength as the coatings grow together. The amount of strength attained by the mixture of cement and water depends on how effectively the space between the grains is filled up. Concrete will harden within a few hours, but hydration continues for weeks, even years after placement. Here is a picture of cement particles before exposure to water. Dry cement is a fine powder, and the particles are not attached to each other. After the cement is mixed with water and allowed to stand, the picture is quite different. Now the particles are grouped together and attached by solid material that provides structural integrity. Scientists at the National Institute of Standards and Technology have learned how to simulate cement hydration on a computer. Using computer simulation, hydration is speeded up to occur in minutes rather than days. Before the hydration simulation, particles of cement are arranged on the computer display. The computer determines regions of the particles that can dissolve into water. The bits of dissolved cement diffuse through the water in a random manner and react to form solid phases according to certain rules. After a cycle of dissolution, diffusion, and precipitation is complete, the computer proceeds with another cycle. As this process repeats again and again, the microstructure develops, building bridges between particles that provide strength. Has proved valuable because it allows researchers to test conditions and make measurements that are difficult to achieve in real life. At the end of the hydration simulation, the structure of the hardened cement paste is very similar to that observed under the microscope. Hydration is an exothermic process which generates heat through chemical reactions. The process of hydration can be easily followed by monitoring the production of heat that accompanies the reactions. This is done by sieving mortar from a batch of concrete and weighing it into a bottle which is placed into an insulated container. A thermistor is then embedded into the fresh mortar. The output of the thermistor can be recorded by a computer. The results of this experiment can be plotted as a curve of temperature versus time. The area under the major peak can be related to early strength development. The initial dissolution of cement produces a short release of heat, shown by the first peak in the calorimetry curve. After the initial dissolution, hydration products are quickly precipitated on the surface of each cement particle. The layer acts as a protective barrier and temporarily delays the further dissolution of the particle. This slows down the reaction for a period of several hours and is called the dormant period. The existence of the dormant period allows concrete to be transported to the construction site and placed and finished in the forms. The end of the dormant period represents the beginning of setting, at which time the cement again starts to react more rapidly with water as new hydration products are formed. Scientists are using measurements of other properties to monitor concrete setting and hardening. Researchers often need to know what portion of the cement has hydrated. The degree of hydration can be estimated by heating a sample of cement paste and measuring weight loss as a function of temperature using thermogravimetric analysis equipment. The free water in a sample is driven out by heating to 105 degrees Celsius. At 105 degrees, the sample is dry, but still retains its strength. The water involved in the hydration reactions is chemically combined with the cement and can be driven out of the sample by heating to 1,000 degrees. At 1,000 degrees, all of the original mix water has been removed from the sample. The degree of hydration is calculated from the weight of chemically combined water. A typical cement paste cured in moist conditions will reach a degree of hydration of about 80% in 28 days. The electrical properties of cement or mortar samples can be followed over time, leading to profiles of changes in electrical resistance. The electrical properties of this cement specimen are being measured using the two metal electrodes. This chart illustrates how the resistance of electricity through the cement increases as the cement hydrates. At early ages, the water easily conducts current across the specimen. But when hydration products fill in the open spaces within the specimen, electrical current cannot pass as easily. In this way, the electrical properties can be related to the degree of hydration. The resistance and impedance of cement is a topic of research that may someday change the way we test fresh concrete in the field. The fluid properties of concrete are very important in the field because quality construction demands adequate consolidation. The standard slump test provides a coarse measure of concrete workability. This test is widely utilized because it is easy to conduct in the field. Fluid properties are also the subject of research in the lab because the flow of cement changes as hydration proceeds. Properties such as viscosity and the initial resistance to flow are used to characterize liquid materials. Water is a liquid with low viscosity and a low initial resistance to flow. But concrete, mortar, and fresh cement paste have much higher viscosity than water. Vibration is often used to overcome this resistance in concrete. In the lab, fluid properties of cement paste can be measured with this Brookfield rheometer. Researchers use larger equipment, such as this Tattersall rheometer, to measure the properties of mortar and concrete. The rheological equipment can be used to measure the initial resistance to flow, which is referred to as yield stress. At the time of setting, the yield stress starts to increase abruptly, and the ability to flow is lost. Researchers are interested in flow characteristics of concrete and leads to set in the concrete. The rate of hydration can be controlled several ways. Factors such as temperature, cement type, and admixtures influence the rate. One of the most important variables is the ambient temperature. High temperatures speed up hydration so that setting is faster, as well as subsequent strength development. The opposite occurs when the temperature is lowered. A good rule of thumb is that for every 10 degrees Celsius change in temperature, the rate of hydration is changed by a factor of 2. For example, an increase in temperature from 20 degrees Celsius to 30 degrees Celsius doubles the rate of hydration. It is important to remember that when the weather gets cooler, concrete is slow to harden and must be kept in forms for a longer period of time. Hydration of concrete can also be controlled by using different types of cement to counteract the effects of high or low temperatures in the field. For example, the use of type 3 cements counteract cold temperatures because they hydrate faster. There are also special chemicals that regulate hydration. Accelerators can be added to concrete to make hydration proceed faster. Set retarders slow hydration. These materials are widely available. In summary, hydration is a chemical reaction between the cement and water that bind the cement particles and the aggregate in concrete into a strong, enduring mass. One of the important advantages of concrete over other construction materials is that it is mixed and formed on site, and it can take on very large and flexible shapes. The ability of concrete to quickly gain strength makes it a valuable material for roads, buildings, bridges, and other important structures.